How common are Earth-like planets in the universe? When scientists first began studying supernova explosions, few expected this work to lead to a question about the origin of planets like Earth. But over time, the connection became impossible to ignore. For decades, planetary scientists have believed that the early solar system was enriched with short-lived radioactive elements, especially aluminum-26, delivered by a nearby supernova. These radioactive elements played a crucial role in shaping rocky planets. As they decayed, they heated young planetesimals, causing them to lose much of their original water and volatile materials. This process helped form water-depleted worlds like Earth. But there was a problem. The traditional explanation requires an extraordinary coincidence. The supernova must explode at exactly the right distance, close enough to deliver radioactive material, but not so close that it destroys the fragile protoplanetary disk. The geometry must also be perfectly aligned for the material to be injected efficiently. In short, Earth's formation seemed to depend on an event that was possible, but extremely rare. As researchers studying supernova physics and cosmic rays, this explanation felt incomplete. Supernovae are not just massive explosions, they are also among the most powerful particle accelerators in the universe. Their shock waves generate vast numbers of high-energy particles, known as cosmic rays, which travel far beyond the expanding debris. Yet, in most models of planet formation, these cosmic rays were largely ignored. So, a new question emerged. What if the young solar system wasn't just hit by supernova debris, but was also immersed in a constant bath of cosmic rays? In a recent study published in Science Advances, researchers explored this idea using numerical simulations of cosmic ray acceleration and nuclear reactions. When cosmic rays interact with a protoplanetary disk, they can trigger nuclear reactions that naturally produce short-lived radioactive elements, including aluminum-26. The results were surprising. The required amounts of radioactive material can be produced at distances of about 1 parsec from a supernova, a distance that is common in star-forming clusters. At this range, the protoplanetary disk remains intact. No perfectly timed injection is needed. The young solar system simply had to form in the same stellar nursery as a massive star that later exploded. This process is called a cosmic ray bath. Unlike rare injection events, cosmic ray baths are likely universal. Many sun-like stars form in clusters, many clusters contain massive stars, and many massive stars eventually explode as supernovae. If cosmic ray baths are common, then the internal heating processes that shaped Earth may also be common. This changes how we think about Earth-like planets. If Earth required a nearly miraculous supernova encounter, then worlds like ours might be rare. But if cosmic ray immersion is enough and widespread, then the conditions that shaped Earth could arise around many sun-like stars across the galaxy. This doesn't mean every planet becomes habitable. Disk lifetimes, stellar dynamics, and many other factors still matter. But it does suggest that Earth's formation may not have depended on an almost impossible coincidence. Sometimes, the key to understanding where we come from isn't adding more complexity, but realizing what we've been overlooking.